X-ray diffraction by crystals. So X-ray diffraction is a scattering of X-rays by the units of a crystalline solid. The scattering or diffraction, the patterns produced, are used to deduce the arrangement of particles in the solid state. It is the result of the interference of the waves associated with the X-rays by the lattice points in the crystal. And in this diagram you can see the setup for how X-ray diffraction is done. So mathematically, 2 times the distance times the sine of the angle is equal to n, which is an integer, times the wavelength. That n value will be given to you in the problem, and then you'll either be solving for wavelength, angle, or distance. So in this example, we're given wavelength in nanometers. We're given the angle, and we're given the value of n. So we want to calculate the distance in picometers. So we do have to do some adjustment as far as our units are concerned. So let's take our nanometers and convert it to meters. So we know 1 nanometer is times 10 to the negative 9th meters. So that gives us 1.54 times 10 to the negative 10th meters. Then let's plug this into the formula. 2 times the distance, was what I'm looking for, times the sine of 14.17 degrees equals 1 times 1.54 times 10 to the negative 10th meters. And then just solve for the distance. And x would equal 7.7 times 10 to the negative 10. Negative 11 meters. But they want it in picometers. Well, we know that 1 picometer is 1 times 10 to the negative 12 meters. So that would give us a distance of 77.0 picometers. X-ray diffraction technique offers the most accurate method for determining bond lengths and bond angles in molecules in the solid state. Because X-rays are scattered by electrons, an electron-density contour map can be made. The map tells us the relative electron densities at various locations. From that, we can tell where the nucleus position can be, and therefore we know the parameters of the molecule. Types of crystals. The structure and property of the crystals are determined by the kinds of forces that hold the particles together. So there's 4 major types: ionic, covalent, molecular, and metallic. Ionic crystals are composed of charged species, so you have positives and negatives. Anions and cations are different sizes, so we can get them to be close together based on their size. Remember, anions gain electrons, so they tend to be the larger molecules, and cations shrink, so they are the smaller ones. So how many Na and Cl ions does each NaCl unit have? So here we have our structure of sodium chloride. Notice that the chlorines are in each of the corners. Well, if they're in each of the corners, I know that that contributes 1 atom total, because each corner is 1/8 of an atom, and there's 8 corners. Each chlorine is also on the face of the atom, so I know that that is going to be 6 faces, and they contribute half, so that is 3 atoms total. So there are 4 chlorine atoms, or chlorine ions, for each unit cell. Now there's the sodium ions are on the edges, and the edges contribute 1/4 of an atom. So the sodium is on each of the edges, and there's 12 edges, so that's 3 atoms total. So the sodium chloride ion is actually made, or a unit cell, is made of 4 chloride ions and 3 sodium ions. Copper crystallizes in a face-centered cubic cell, or cubic lattice. If the density of the metal is that, what's the unit cell edge length in picometers? So we know that density is equal to mass over volume. And to find the edge length, I know that volume is length cubed. It's a perfect square, so length, width, and height should all be the same. So what I need to do then is to solve for the volume and then solve for the length. So to solve for the volume, I have to know the mass. Well, because it's face-centered cubic, I know that I have 1 atom coming from the corners, plus I have 3 atoms coming from the faces. So I have a total of 4 atoms of copper made up in that unit cell. So we'll take 4 atoms of copper, Avogadro's number of atoms is 1 mole of copper, and 1 mole of copper is 63.5 grams of copper. So we have a mass of 4.22 times 10 to the negative 22nd grams. So using my density formula, the volume then would equal my mass divided by my density. And so I get a volume of 4.71 times 10 to the negative 23 centimeters. I want the edge length though, so this is the volume. So if I take the cubed root of that, I would get my length. So my length ends up being 3.61 times 10 to the negative 8 centimeters. Now it doesn't want centimeters, it wants it in picometers. So I have to do some converting of units. I know that 1 centimeter is 1 times 10 to the negative 2nd meters, and that 1 times 10 to the negative 12th meters is 1 picometer. So I get an edge length of 361 picometers. Most ionic crystals have high melting points because of the strong cohesive forces holding the ions together. The measure of the stability of the ionic crystal is the lattice energy. Remember, we talked about that in a previous unit. The higher the lattice energy, the stronger and more stable the compound. Ionic crystals do not conduct electricity as solids because the ions are in a fixed position. But if they're in the molten state or dissolved in water, the ions are free to move and the liquid is electrically conducting. Covalent crystals are atoms that are held together by an extensive 3D network entirely by covalent bonds. These tend to be made of carbon or silicon. So in picture A, that's actually a diamond with the tetrahedral shape around the carbon. In picture B here, we have graphite, which is a trigonal planar. Because graphite is trigonal planar around the carbon, it has pi bonding, and the pi bonding, being parallel bonding, allows electrons to flow and move, and it actually creates a delocalized type of bonding because of they're all pi bonding. So it conducts electricity, where in our diamond, because it's tetrahedral, it's all sigma bonds overlapping, the electrons aren't moving, so diamonds don't conduct electricity. In the third picture, that's silicon dioxide, or quartz. Molecular crystals have the lattice points are made by molecules, and the attractive forces between them are van der Waals and or hydrogen bonding. With the exception of ice, molecules are packed tightly closely as their size and shape allow. Ice is different because of the number of hydrogen bonding allowed by the water. So if the intermolecular forces are considered weaker, therefore they're more easily broken apart than the ionic or covalent crystals. In this picture we have sulfur. Remember, sulfur is actually S8, so we have a molecule of S8 at each of our lattice points. Metallic crystals. Every lattice point in the crystal is occupied by an atom of the same metal. They're generally bonded body-centered cubic, face-centered cubic, or hexagonal closed pack. That means that they're usually very dense and they have great cohesive forces resulting from the delocalized valence electrons, which is responsible for the metal's strength. The mobility of the electrons also make the metals a good conductor. So metallic bonds or metallic crystals, metallic solids, are the only ones that conduct electricity in the solid state, with the exception of our network covalent graphite. Amorphous solids are solids that are most stable in the crystalline forms are the most stable. Amorphous solids are a little less stable, and that's because it's formed rapidly when atoms and molecules don't have enough time to align themselves. So they lack a three-dimensional arrangement of atoms. Two examples that you should be aware of are glass and plastics. Glass is an optical transparent fusion product of inorganic materials that is cooled to a rigid state without crystallizing. Glass is mixing molten silicon dioxide with compounds like sodium oxide or boron oxide or other metal oxides. If the metal oxide has a transition metal in it, then you could have colored glass. So glass actually acts more like a liquid than a solid. If you ever find a really old piece of glass, like in a window pane, the window pane at the top is thinner than the window pane at the bottom, and that's because it's a supercooled liquid, so the glass actually gets pulled down by gravity. Where if you look at a really old structure of steel or brick, it doesn't have that gravity effect. In picture A, you can see regular silicon dioxide, and then in picture B, you can see what it looks like when it's cooled rapidly. Now, if you've ever heard about making glass at the beach, lightning bolt hits the beach and it makes glass. That's because the lightning bolt heats up the sand, which is silicon dioxide, very quickly, and then it cools very quickly, and you get a piece of glass.